Hello everyone, my name is Zaiwei Chen. I'm from Georgia Institute of Technology. Today I'm going to talk about our work finite sample analysis of stochastic approximation using smooth convex envelopes. This is a joint work with my co-advisor Professor Maguluri from Georgia Institute of Technology, Professor Shakkottai from the University of Texas at Austin, and Dr. Shanmugam at IBM Research, New York. To motivate the study of the stochastic approximation algorithm, I will first introduce the Markov decision processes and the reinforcement learning problem. In a Markov decision process, at time k, the agent is at a certain state of the environment, call it Sk, and the agent is allowed to take some action Ak according to a chosen policy pi. Then the system dynamics will drive the agent to a new state Sk plus 1 and return the agent a stage-wise reward. The goal is to find a policy which maximizes the expected long-term reward. Reinforcement learning problem is essentially a Markov decision problem, except that the dynamics of the system, that is, the transition probabilities and the reward function, are unknown. The performance of a policy pi is measured by its value function, which is defined to be the expected total reward the agent would receive if the policy pi is used. Since the underlying transition probabilities are unknown, a sub-problem of reinforcement learning is to estimate the value function, which is called the policy evaluation problem. Similarly, the state action value function, also known as the Q function of a policy pi at state action pair SA, is defined to be the expected total reward starting from the state S, first taking the action A, and then following the policy pi thereafter. It is well known that once the optimal Q function is obtained, the optimal policy can be directly obtained by just selecting actions greedily based on the optimal Q function. In this case, solving the reinforcement learning problem reduces to estimating the optimal Q function. It turns out that both the state value function and the optimal Q function satisfy a certain fixed point equation, which is called the Bellman's equation. Take the Bellman's equation for the Q function, for example. The left-hand side is the expected total reward starting from the current state action pair, and the right-hand side is a combination of the one-stage reward and the discounted future reward. By properly defining the operator H, we see that both Bellman's equations reduce to a fixed point equation of the form x equal to h of x. Note that the operator H involves the expectation with respect to the underlying Markov decision process. Since the underlying transition probabilities are unknown, the operator H is unknown to us. So the problem is to find the solution x star to the equation x star equal to h of x star. Suppose that there is an oracle such that for every x, it returns the exact value of h of x. Then the solution x star can be estimated by the following fixed point iteration. When the operator h is a contraction with respect to some arbitrary norm, call it C norm, that is, the distance between h of x and h of y measured in C norm is less or equal than gamma times the distance between x and y, where gamma is a contraction factor and it is between 0 and 1. Then we can show that the iterates xk generated by the fixed point iteration converges to x star geometrically fast. Now suppose that such an oracle is corrupted by noise. That is, for a given x, it does not return h of x, but returns h of x plus some noise, call it w. Then the fixed point iteration becomes the following stochastic iterative algorithm, where wk stands for the noise sequence, and it is added to the update. The asymptotic convergence of this stochastic approximation algorithm is studied in the literature. Our goal here is to provide the finite sample convergence guarantee. To study this stochastic approximation algorithm, we make the following two assumptions. One is that the operator H is a gamma contraction with respect to some arbitrary norm. The other is that the noise sequence is a martingale difference, which means that it is conditionally mean zero. Moreover, we assume that its conditional second moment grows at most affinely in terms of the current iterate. In existing literature, usually it is assumed that the noise is uniformly bounded by a constant. We relax that assumption here. We next state our results. We first consider the case where we use constant step sizes in the stochastic approximation algorithm. We show that for properly chosen step size, the mean square error can be bounded above by the two terms on the right-hand side. The first term kind of represents the bias in the iterates, and we see that it goes to zero geometrically fast as the number of iterations tends to infinity. The second term represents the impact of the variance. Note that it is not a function of k, which means that even when k goes to infinity, it remains as a constant. The reason is that when using constant step sizes, the noise is constantly added to the iterates without being progressively suppressed. Geometrically speaking, these finite sample bounds indicate that, in expectation, the iterates will converge geometrically fast to a ball centered at the target solution x star, and the size of the ball is proportional to the step size. We next show the finite sample bound for using diminishing step sizes. We choose epsilon k to be alpha divided by k. We show that for properly chosen alpha, the convergence rate is 1 over k. Recall that when using constant step sizes, the bias goes to zero geometrically fast, while the variance remains as a constant. Using diminishing step sizes kind of balance these two terms, and they both achieve 1 over k convergence rate. Now we have presented our results for a general stochastic approximation algorithm. Next, we will show how our results can be applied to reinforcement learning algorithms. The first reinforcement learning algorithm we consider here is the V-trace algorithm for solving the policy evaluation problem. The V-trace algorithm proposed by Esperholt et al. 2018 is a multi-step off-policy temporal difference learning algorithm incorporated with importance sampling. Multi-step means that in each iteration, instead of using the data from only one transition, multiple transitions are used, in this case, capital T transitions. Off-policy means that the policy used to collect samples is different than the policy whose value function we want to evaluate. To correct the difference between them, the importance sampling ratio is introduced. The asymptotic convergence of the V-trace algorithm was established in Esperholt et al. 2018, where the V-trace algorithm was modeled as the stochastic approximation algorithm with a contraction operator, and the noise scales affinely in terms of the current iterates. We next provide its finite sample bound. We consider using diminishing step sizes of the form epsilon k equal to alpha divided by k in the V-trace algorithm. We show that the convergence rate is roughly 1 over k. Importantly, note that the size of the state space, which is S, appears as log S in the bound, which is desirable since usually the size of the state space is very large. The second reinforcement learning algorithm we consider here is the popular Q-learning algorithm for estimating the optimal Q function. It is shown that the Q-learning algorithm can also be modeled as a stochastic approximation algorithm with a contraction operator, and the noise satisfies our assumption. Similarly, when using diminishing step sizes of the form epsilon k equal to alpha divided by k, with properly chosen alpha, the convergence rate of the synchronous Q-learning algorithm is 1 over k, and the size of the state action space scales logarithmically in the bound. This result recovers the existing state-of-the-art finite sample bound of the Q-learning algorithm. To conclude, we provide finite sample convergence bounds for a certain stochastic approximation algorithm, which can be used to study several reinforcement learning algorithms. Due to the time limit, I only present the results here. If you are interested in the proof technique, please see our papers on arXiv. Thank you all for listening and looking forward to see you all at the workshop.